Chapter 16 is carboxylic acids and esters, and we're beginning with section 1, which is just carboxylic acids. The carboxylic acid contains a carboxyl group, which is really a carbonyl with an OH group attached to it. So you have to be very careful about identifying these compounds because they contain functional groups that we've seen as characteristic of other compound types previously. In this section, we're again going to learn the IUPAC naming system for these, as well as how to draw their condensed structural and line angle formulas. In the IUPAC naming system for carboxylic acids, you simply drop the E at the end of the alkane chain and replace it with oic acid. So methane is a 1-carbon alkane. When you take that carbon and you turn it into a carboxylic acid by making it double bonded to an oxygen and then bonded to an OH, instead of methane, we drop the E and turn it into methanoic acid. With ethane, we drop the E and we call it ethanoic acid. Just like aldehydes, the carboxylic acid group always has to be a terminal carbon. It can't be anywhere in the middle of the chain. And so that means it's always going to be counted as carbon number 1, but we never need to include the number. So for methanoic acid or ethanoic acid, it may be obvious that there's only one possibility there. But even in propanoic acid or 2-methylpropanoic acid or longer acids, it's always going to be on the first carbon, and so we don't need to call it 1-propanoic acid. It's just propanoic acid. When a carboxylic acid group is attached to a benzene ring, like you see here, this is specifically called benzoic acid. And this is another special case of an aromatic derivative that you need to remember the specific name for. As with phenol, the carbon where the functional group attaches is carbon number 1. In phenol, the functional group was an OH. Here, it's an entire COOH group. But nevertheless, the carbon where it attaches is number 1, and then you again count the shortest distance to any other substituents that are present. So this would be 3,4-dichlorobenzoic acid. Here, the bromine is on the 2-carbon, and so it's 2-bromobenzoic acid. Once again, ignore the common names for any of these compounds. You don't need to know any of the common names for carboxylic acids or any of the other compounds. But there are two things you might want to keep in mind. First is that you may see prefixes like these, form, acet, propione, or butyra. These are the prefixes used in some common names of compounds, and they can sometimes look like they're just misspelled forms of other prefixes or base names that we've learned about, but they're not. It's a totally different system, so you may come across those, and you should just be aware of that. The other thing that is sometimes useful to know is that with common names, there's typically an alternate system for numbering or labeling the chain of carbons. So in the normal system, we would just start with the carboxylic acid carbon as number 1, and then we would just number from there. But there's another system where we ignore the carboxylic acid carbon, and we just count the first carbon attached to it as the alpha carbon. Alpha is the first letter in the Greek alphabet. And so after that, we would go through the Greek alphabet in order. So the next carbon after that would be beta, and then the next carbon after that would be gamma, and then the next carbon would be delta, and so on. So there are a couple of naming conventions for compounds later on that we'll see that are based on this Greek letter system. So it might be useful for you to keep that in mind for now. But again, you don't need to know the common names. These are just two things that you may run into, and so you should be aware of them. Carboxylic acids are relatively common in nature. So, for example, the sting of a red ant contains methanoic acid, which is a skin irritant. Methanoic acid is more commonly known as formic acid. This comes from the Latin word for ants, which is formica. It's not related to the common building material, but it is the root of this word, formic acid, as well as compounds with common names like formaldehyde. The sour taste of vinegar, on the other hand, is due to acetic acid. We've talked about this a few times, but acetic acid is more properly known as ethanoic acid. It's a 2-carbon chain with a carboxylic acid on the end. So let's take a look at this example. Here we're given the structure of an organic compound, and it says, give the IUPAC name for the following carboxylic acid. We can see that this COOH group here is what makes it a carboxylic acid. And we can also see that it's part of a 3-carbon chain. So remember, the carbon in the carboxylic acid is the first carbon, then this would be the second, and this would be the third. So we have a 3-carbon chain, which would be propane, but as a carboxylic acid, we would call it propanoic acid. And then we also have this substituent here on the second carbon, so we add that as a prefix. So it will be 2-methyl propane, but then we drop the E from propane and make it propanoic acid. 2-methyl propanoic acid. Here we have 2 structures, and we're asked to find the names for each of them. In this case, the carboxylic acid is here. In this case, it's here. In the first example, you have the carboxylic acid carbon is number 1, this is 2, this is 3, and this is 4. So that makes this butane or butanoic acid as the derivative. This methyl group is on the 3rd carbon, so it's 3-methyl butanoic acid. Don't forget there's a space between butanoic and acid. In this one, we have a carboxylic acid, but it's attached to a benzene ring. So instead of focusing just on the acid, we should actually look at this entire structure and remember that this is called benzoic acid. Where the carboxylic acid attaches is carbon number 1, and then we count the shortest distance to the next substituent, which is the bromine atom. That's on the 3rd carbon, and so this is 3-bromo-benzoic acid. And again, there's a space right before acid. Next, we're asked to draw the line-angle formula for 4-chlorohexanoic acid. The line-angle formula means we start with a zigzag. So this is 1 carbon where you put your pencil down. That's 2, 3, 4, 5, 6. We know that the carboxylic acid has to go on either the first carbon or the last carbon, so I can put it here, make this a double bond to an oxygen, and then this has to go to an OH, so this is our carboxylic acid carbon. And then we need to put the chlorine group on the 4th carbon, so this would be 1, this would be 2, this would be 3, and then this would be 4, so the chlorine group can go here. So this is the structure for 4-chlorohexanoic acid. Carboxylic acids can actually be prepared from what are known as primary alcohols or aldehydes. A primary alcohol is an alcohol where the OH group is on a terminal carbon. So in this example, we have ethanol. Ethanol, we saw, could be produced from the fermentation of sugars or grains, but if that fermentation process is taken too far, the additional oxidation steps can convert this primary alcohol, ethanol, into first an aldehyde, where this would be called ethanal, and then another step would bring it to become a carboxylic acid, in this case ethanoic acid, or more commonly known as acetic acid. So again, this acetic acid is a contaminant in fermentation, which gives a sour, unpleasant odor or taste to your alcohol. Alpha hydroxy acids are natural products that are found in substances like fruits, milk, and sugarcane. And these are naturally occurring carboxylic acids that have additional hydroxyl groups in a certain position on them. We'll see in a second. But these have also been acknowledged to be helpful for skin and to prevent aging by dermatologists for some time. So they're in a lot of health and beauty aids that you might find in the store. So here we see some examples of the structures of alpha hydroxy acids. And this is one example where the alternate numbering system for the carboxylic chain comes into effect. So instead of numbering the chain 1, 2, 3, 4, we start with the carbon right next to the carboxylic acid carbon, and we call that the alpha carbon. So in this case, you have a carboxylic acid here, which would make this carbon the alpha carbon. And so we have an OH, or a hydroxy group, attached to the alpha carbon. So this is an alpha hydroxy acid, and that's where the name comes from. Here you can see again a carboxylic acid. This would be the alpha carbon, and you have an OH group attached to it. Here you have a carboxylic acid on this side, as well as one on this side. Each of these has a carbon next to it, a carbon that is alpha to it, and each of those alpha carbons has a hydroxyl group on it. Here we see only one of the alpha carbons has a hydroxyl group, but it still fits the naming system. And in this last one, we can see actually citric acid, where you have a carboxylic acid here, this carbon would be alpha to it, and then here is a hydroxy group attached to it. Citric acid is a naturally occurring carboxylic acid that has actually 3 carboxylic acid components, and this is part of the flavor and acidity of citrus fruits.